In this video, we solve problem 9.10.065 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to use a power series to approximate the value of the integral with an error of less than 0.0001. We're asked to round our answer to 4 decimal places. Now, this function is a pretty nice function. It's well defined except for when x is equal to 0. But I don't know if you remember from Calculus 1, but the limit of this expression as x approaches 0 is a 0 over 0 indeterminate form. And if we use L'Hopital's rule, we can prove that the limit is equal to 1. I wanted to show you just a picture of what it is that we're looking at and what it is we're trying to estimate, and then we will use Taylor's series Maclaurin series in order to evaluate this expression. So just briefly, let me share my screen with you, sort of show you what it is we're looking at. So this is f of x equals sine of x over x. Notice that when x is equal to 0, there is, it looks like y is equal to 1, but there actually should be a little hole in the graph there because obviously this is not defined when the denominator is 0. And as x goes to infinity, you've got this number between -1 and 1 divided by something that is very large in magnitude. And so it sort of damps out and it gets closer and closer to the y-axis. But we're interested in the area under the curve here between x equals 0 and x equals 1. Now we can find that area if we come up with a Maclaurin series expression for this integrand and then evaluate the Maclaurin series at 0 and 1 and subtract. Now that's going to give us an exact answer, and it's going to be a Maclaurin, well, it won't be a Maclaurin series anymore because we will have evaluated it at x equals 0 and x equals 1 and we'll be subtracting. But it'll be a series that represents this expression here. And if we have infinitely many terms, we can get this exact blue area here. But we don't want the exact answer. We just want to take a number of terms so that the error is less than this 0.0001 that they gave us. So we're just going to use Taylor's formula to find the appropriate number of terms so that our error is less than 0.0001. Actually, on second thought, I might not even need to use Taylor's formula for that. Okay, so the first step is to find a Maclaurin series for this function. Oops. Well, and that's easy enough to do. We just take the Maclaurin series for sine of x, which we know looks like this. It's an odd function. Gets all the odd terms. Got a -1 to the n here. And if n is an integer, 2n plus 1 is odd. We're dividing by 2n plus 1 factorial. So this is sine of x. We expand this, we have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus higher order terms. We're going to take each of these guys and we're going to divide by x. So that's like multiplying by a 1 over x here. So I'm taking this and dividing by x, which is the same as taking this series, taking every term in this series and dividing it by x. Well, we remember from pre-calculus that if you've got x to some power over x to a different power, you just subtract the exponents. That's legal and appropriate, provided that the this base x is not equal to 0. So if I've got x to the 2n plus 1 and I'm dividing all of those by x, what I'm going to end up with is x to the 2n. So we'll have -1 to the n times x to the 2n over 2n plus 1 factorial, which is exactly what we get over here. X divided by x is 1. Then we'll have x squared over 3 factorial plus x to the 4th over 5 factorial minus x to the 6th over 7 factorial, because we're just taking each of these powers of x and we're decreasing them by 1 because we're dividing by an x. So this is the series, but I guess we should add that this is the series for this, provided that x is not equal to 0. If x is equal to 0, this is undefined. But we can also see, now if we were to plug in 0 to this, we would get a 1 here. So the limit of this expression as x approaches 0 is going to be 1, which is just what we saw in the picture over there. Okay, so this is our expression for the integrand. We want to evaluate the integral of this, and then we'll evaluate that expression at 0 and 1 and subtract. So the integral from 0 to 1 of sine of x over x is equal to the integral from 0 to 1 of this expression, because that is another way of writing sine of x over x. Since we've got a jump discontinuity at x equals 0, we don't really need to write this as an improper integral, although technically it is an improper integral. We could let a approach 0 from the right. Let's do it. Let's do it the right way. I was going to take a shortcut. I probably shouldn't. Let's take the limit as a approaches 0 from the right of the integral from a to 1 of this infinite series. And then I'm ignoring this limit for right now. And then here I'm just anti-differentiating term by term, just like I would here. So I would add 1 to the exponent and divide by the new exponent for all of these. So I'd get x cubed over 3 factorial, or x cubed over 3 times 1 over 3 factorial, x to the 5th over 5 times 1 over 5 factorial, plus x to the 7th over 7 times 1 over 7 factorial, and so on. The shorthand for that is this. We'll add 1 to this exponent. I keep picking up these pens. They're black pens that have the wrong color cap on them. And then we'll divide by the new exponent. And this 2n plus 1 factorial is still in the denominator. And then we'll evaluate this from x equals a to x equals 1, and then we'll subtract. At x equals 1, that's just going to be a 1. So you have the sum as n goes from 0 to infinity of -1 to the n over 2n plus 1 times 2n plus 1 factorial, minus, when x is equal to a, this expression. We're just replacing the x with an a. And then we evaluate this limit as a approaches 0 from the right. And when n is equal to 0 here, we get -1 to the 0, which is 1, a to the 1, so it's a to the first, over 1 times 1 factorial. So when n is equal to 0, we just get an a here. And then we've got, obviously, higher powers. We're going to have a, and then we're going to have an a cubed term and an a to the 5th term and an a to the 7th term, and so on, because that exponent will always be odd. But as a approaches 0, all of those are going to go to 0. So this guy goes to 0. And this guy doesn't involve a. So the value of this integral from 0 to 1 of this function is the value of this improper integral. And it's the sum as n goes from 0 to infinity of -1 to the n over 2n plus 1 times 2n plus 1 factorial. Or if we expand, when n is equal to 0, we'll get 1 over 1 times 1 factorial. When n is equal to 1, we'll get -1 over 3 times 3 factorial. Then when n is equal to, this n is equal to 0, this is n is equal to 1. When n is equal to 2, we'll get negative 1 squared, which is positive 1, over 5 times 5 factorial. Notice that you've got two odd numbers. One of them has a factorial, the other one doesn't. And then you're alternating between positive and negatives here. So we've got positive, negative, positive, negative, positive, and it would continue in this way. And in the denominator, we've got 1 times 1 factorial, 3 times 3 factorial, 5 times 5 factorial, 7 times 7 factorial, 9 times 9 factorial, and so on. And the question asked us to approximate the value of the series, or approximate the value of the integral with an error less than 0.001. Well, one thing that I notice about this is that this is an alternating series because of this positive, negative pattern. So we can use the alternating series estimation theorem here. And so that's going to give us an upper bound on the error for an expression that looks like this. Okay, I guess in this textbook it's called the alternating series remainder theorem. So it says, if we have a convergent alternating series that satisfies the condition that the n+1th coefficient of this here is less than or equal to the nth coefficient. So this is where we're thinking of this as the sum as n goes from 0 to infinity of -1 to the n times b to the n, or b to the n is the absolute value of this term. So it says, if we have a convergent, let me write it down, alternating series that satisfies this condition. So b sub n plus 1 is less than or equal to b sub n. So whatever it is we're adding or subtracting next is always smaller than the number that we were adding or subtracting before. So this 1 over 3 times 3 factorial is smaller than this guy. And this 1 over 5 times 5 factorial is smaller than 1 over 3 times 3 factorial. And this one is always smaller than that. If that's satisfied, and it is for this, in our case, b sub n plus 1 is equal to this, or b sub n is equal to that, which means that b sub n plus 1 is equal to this. If I replace n with n plus 1, I'll have n plus 1 times 2 is 2n plus 2, plus another 1 is going to be a 3. And that's consistent with what we see up here. But since the denominator is larger here, the fraction is smaller. So this is definitely smaller than this, which is what's required for us to use this theorem. Okay. It says then the absolute value of the remainder in approximating the sum s by the nth partial sum is always less than or equal to the first neglected term. So that means the actual sum of the series minus the nth partial sum. That's just, a truncated version of this. That's called the remainder for that nth partial sum. And that's always equal to the next term, the absolute value of the next term. So we're ignoring the sign. We're going to call that b sub n plus 1. Okay, so b sub n plus 1 in this case is equal to that. 1 over 2n plus 3 times 2n plus 3 factorial. And we want that number to be less than or strictly less than 0.0001. So we have to find the value of n that causes that expression to be less than 0.0001. And I wish I could tell you that I had a very sophisticated way of finding that value for n, but I really don't. All I have for you is, let's say when n equals 1, we have the remainder for r sub 1 is less than b sub 2. And b sub 2 is what we get when we evaluate this at, or excuse me, let's do n equals 0 here. So the remainder, when we just use this first term as an approximation of the sum of that series, is going to be less than or equal to the next term. So that's 1 over 3 times 3 factorial. When n is equal to 1, that's giving us this remainder. So that's using this sum, this plus this. Well, that is going to be off by no more than b sub 2, which is what we get when we plug in n equals 2, 1 over 5 times 5 factorial. So I'm just going to write out a few of these. I think we can see the pattern. It's basically the next term. Here I'm using just that 0th partial sum, which is 1 over 1 times 1 factorial, which is just 1. The first partial sum is 1 minus 1 over 3 times 3 factorial, or 1 minus 1 over 18, or 17 over 18. Here we'd have 1 minus 1 over 3 factorial, 3 times 3 factorial plus 1 over 5 times 5 factorial. So that's 1 minus 1 over 18 plus, what's 5 times 5 factorial? I don't even know. Let's see. So I'll do 5 factorial in my calculator. That's 120 times another 5. Okay, 600. And we could get a common denominator if we wanted to, and we could simplify that if we wanted to, but I'm not going to. But the next term is that 1 over 7 times 7 factorial, if we're just looking at the absolute value, and that's the error. We're looking for this number to be less than or equal to 0.0001. So we'll just evaluate those expressions now. Well, we just said that this was 1/18th. So let's see how small 1/18th is. It's approximately 0.5 repeating. Well, it's exactly 0.5 repeating. 0.05 repeating. That's greater than that. Okay. And then I've got 1 over 600 here. That's 0.0016, still larger than that. And then we've got 1 over 7 times 7 factorial here. So I'll do 7 times 7 factorial. That's that number, 1 divided by that answer. Is that fraction? Which is still, was that what? Oh, it is smaller because this only has 3 zeros and this one has 4 zeros. So we've got 0.00028 and so on, and it keeps going. There's more to it than that. But this one is less than that error. So what did the question say? It says, use a power series to approximate the value of the integral with an error less than this value. Well, my error is less than that value or my upper bound for the error is less than that value, when I use the second partial sum here. So we will compute that. So I've got 1 minus 1/18th plus 1 over 600. And we can get a decimal approximation for that. So that's 0.9461 repeating. And I'm not 100% sure what they want in WebAssign, but they do say to round to 4 decimal places. Well, actually, I know that they want that. So just take that and round to 4 decimal places. So the answer we'll type into WebAssign is 0.9461. And again, that 0.9461 is an approximation to the area under this curve given by the function f of x equals sine of x over x on the interval from 0 to 1. So we don't even need to know how to compute the antiderivative of a function that looks like this, sine of x over x. It turns out all of the antidifferentiation rules that we studied in chapter 8 are not going to work for sine of x over x. But we can still approximate the value of that expression doing what we just did here. Now, it does also happen to be that improper integral, which was easily handled because the limit as a approaches 0 of this expression is just 0, and it just disappears because it's approaching 0 as a goes to 0 from the right. So I hope that helps.